Alrighty, howdy folks. The next thing we will look at is translation theorems and derivatives of transforms. In this chapter, I think this is the most important section. It's a bit on the longer side. So with that warning, please brace yourself. It's not intellectually all that difficult, but pretty long. Quite a few concepts are covered. All right, without much further ado. Man, I can never say that phrase quite well. It always feels funny when I say it. Anyway, first translation theorem is as simple as Laplace of e to the at times f of t equals f of s minus a. What? F of s minus a? Yeah, if we were to take Laplace of f of t, what do we get? We get uppercase f of s. You agree with that? Laplace of lowercase f of t is uppercase f of s. However, if you multiply that f of t with a e to the at and you take the Laplace of that, what you need to do is find the f of s as if that e to the at didn't exist. Find that f of s, but apply a shift. What do I mean by apply a shift? You replace the s with an s minus a. And that's exactly what this part is saying. Laplace of f of t, figure that out, and replace the s with an s minus a. That's what f of s minus a is. Well, can you figure out why this is called first translation theorem? What has translation got to do with anything? Think about it. If you have a function f of s, if you have the graph of a function f of s, and you want to find the graph of f of s minus a, let's say without any loss of generality, a is a positive number. What would the graph look like? Do you remember from pre-calculus or whenever that all you need to do is take the graph of f of s and translate it, move it, shift it to the right by a units, right? See, that's the whole idea. So basically this is a translation theorem because f of s is being translated to the right by a units if a were to be positive. That's all. Okay. Next, proof. It must be a simple proof. That's why I must have added it. Let's see. Laplace of e to the at f of t. If we apply the definition of Laplace transform, that's just the integral 0 to infinity e to the negative st times whatever we are taking the Laplace of, right? So that's the idea. And now you can see that we can rewrite this e to the negative st times e to the at as e raised to negative of the quantity s minus a times t, right? And if I were to say, now pay attention, if I were to say this is nothing but f of s minus a, would you agree with that? What? Check this out. If we have Laplace of f of t, is that f of s? What is Laplace of f of t? E to the negative st times f of t dt. What is that? Laplace of f of t is f of s, and f of s is nothing but e to the negative st times f of t dt. So if we have e to the negative of pt, f of t dt, some p, then we would say uppercase f of p. Would you agree? Think about it. E to the negative pt f of t dt would be uppercase f of p. So here that p happens to be s minus a, so we should say f of s minus a, as simple as that. If you got it, fine. If you didn't get it, don't worry too much about it. All right, so this is the proof of that one. And let me solve a few problems to solidify this concept. How do we find Laplace of e to the 2t times t minus 1 the quantity square? Does this look like Laplace of e to the at times f of t? That's the way to think about all of these things. Does it have that form? What form is it in? Well, can we figure out a immediately? E to the 2t times t minus 1 the quantity square. Yeah, a is 2. F of t is t minus 1 the quantity square, right? So according to this, what should we do? We need to find Laplace of f of t, that is Laplace of t minus 1 the quantity square, and then apply a shift, s shifted by s minus a, or s replaced by s minus a happens to be 2, so s minus 2, right? So that's the idea. Laplace of e to the 2t times t square minus 2t plus 1. And so that is Laplace of t square minus 2t plus 1, to which we'll apply a shift, right? We are accounting for the multiplication by e to the 2t as a shift, s shifted by s minus 2. So we are taking the Laplace of this guy. And that happens to be 2 over s cubed minus 2 over s squared plus 1 over s. And what exactly is shifting means? I said replace the s with a s minus 2 in the next step. That's exactly what I've done. Simple? I think so. Okay, next. Laplace of e to the t cosine square 3t. Does it again look like Laplace of e to the at f of t? It does. What is a? 1. So shift would be s shifted by s minus 1. Laplace of what we should take? Of cosine square 3t, and apply the shift, right? Like this. But the thing is, do we know how to find Laplace of cosine square 3t? Think about it this way. Would you know how to find integral of cosine square 3x dx? You remember, you need to apply a certain identity for it. And that's exactly what we'll do. And the identity is cosine square 3t is 1/2 times 1 plus cosine of 6t. Right? That's what I did. And Laplace of 1/2 is 1/2 times 1 over s. Cosine 6t is s over s square plus 6 square. And we'll replace s with a s minus 1. Cool? There we go. That's all there is to it. All right. Next. Knowing that Laplace of e to the at times f of t is f of s minus a, can we immediately talk about a certain inverse Laplace transform? Can you make an inverse Laplace transform statement based on this one, folks? If you said Laplace inverse of f of s minus a equals e to the at times f of t, you are absolutely right. Laplace inverse of f of s minus a is e to the at f of t. But then there's a slightly better way of looking at it, which is look at f of s minus a as f of s to which some shift has been applied, s shifted by s minus a has been applied. The moment you do that, the s shifted by s minus a part can be accounted for by multiplying by e to the at. Cool. And all we need to do is e to the at times f of t. F of t is nothing but the Laplace inverse of this f of s. Okay, so look at this one. The moment you see that you need to find the Laplace inverse of something of the form f of s minus a, then figure out what f of s is to which this shift has been applied. The reason you do that, or the advantage of looking at f of s minus a as some particular f of s to which a particular shift s shifted by s minus a is applied, is immediately you would know what a is, which means you know e to the at. And you need to get just the Laplace inverse of f of s, multiply that. That's the idea. So I'll do quite a few examples on this one. Cool. Does this look like some f of s to which a certain shift has been applied? Does it look like f of s minus a? What do you think? If you said, yep, that is nothing but Laplace inverse of 1 over s to the 4, to which a shift has been applied, s shifted by s minus 1, you are absolutely right. But why? Why do we need to do that? That is because as such, there is no formula for Laplace inverse of 1 over s minus 1 to the 4. There is a formula for Laplace inverse of 1 over s to the 4, but not for 1 over s minus 1 to the 4. So the whole idea is to be able to express this in terms of Laplace inverse of something that we actually do know. Right? That's the idea. So Laplace inverse of 1 over s to the 4 to which a shift has been applied. Now, how do we account for s shifted by s minus 1? Oh, that means this Laplace inverse of 1 over s to the 4 must have been multiplied by e to the at, a being positive 1. So e to the t times Laplace inverse of 1 over s to the 4. See how clever that is? That's the idea. And Laplace inverse of 1 over s to the 4, if you did problems in the previous section, you know, is t cube over 3 factorial, right? E to the t times t cube over 3 factorial is 6. That's the idea. And what? Completing the square. How many of you hate completing the square? Well, I got good news for you. I'm going to show you a way where it becomes ridiculously simple to complete the square. Cool? Ready? Alright, here is the idea. If you have something of the form x squared plus bx plus c, to complete the square on this, this is the thing you need to do. You need to add b over 2 the quantity square. Okay, can you do that? You add b over 2 the quantity square. Of course, you cannot just set this equal by adding whatever you want. So compensate for it by subtracting the same quantity. So subtract minus b over 2 the quantity square, and we originally had this plus c, so keep it there. Cool? Can you remember that part? If you want to complete the square, add a b over 2 the quantity square and subtract a b over 2 the quantity square. The reason you do that is, or when you do that, this is what happens. The first 3 terms, x squared plus b, that is nothing but x plus b half the quantity square. Okay, so what was not in the form of a perfect square, we obtained a perfect square here. That's why it's called completing the square. And so this becomes x plus b over 2 the quantity square minus b square over 4 plus c. Now, on the other hand, I have an example. Does it look like that? Yep, it does. What is b? 4. So what should we add and subtract? B over 2 the quantity square, that is 4 over 2 the quantity square, and subtract the 4 over 2 the quantity square. See, as a first step, that's exactly what I did. And subtracted 4 over 2 the quantity square, and there was a plus 13, added that 13. Now what perfect square do the first 3 terms make up? 4 over 2 is 2. So this is x plus 2 the quantity square. And this is a minus 4 over 2 is 2, 2 square is 4, plus 13, x plus 2 the quantity square plus 9. That's it. Right? What do we do if we have x square minus 8x plus 20? What is b now? Negative 8, right? Cool. We'll add a negative 8 over 2 the quantity square and subtract a negative 8 over 2 the quantity square. And now the first 3 terms become x minus 8 over 2, x plus negative 8 over 2, or x minus 4, the quantity square. Of course, because we are squaring negative 4, we just get positive 16 for that stuff, but we are subtracting that. So minus 16 plus 20. That's it. You really need to know how to complete the square because there are certain problems involving Laplace inverse that require this process. That's why I digressed and talked about this. All right? Are we good now? All right. Let's move on. Check this out. How do we find the Laplace inverse of this? Piece of cake, right? We split this into partial fractions. And the thing is, no, you cannot split it into partial fractions because the denominator is irreducible quadratic. What is irreducible quadratic? B square minus 4ac is actually less than 0. That means the discriminant is less than 0. So you cannot factor this. Okay, so what should we do? And here is where we need to use the concept of completing the square. The bottom one, do a completing the square on it. And then I'll show you what exactly we need to do after that. So first order of business, completing the square on the bottom, which is add a b over 2 the quantity square, subtract a b over 2 the quantity square. The first three terms form a perfect square of s plus 3 the quantity square. This is minus 9 plus 34 is 25. So this reduces to Laplace inverse of 2s plus 5 over the quantity s plus 3 square plus 5 square. Cool? Is there a Laplace inverse formula for something that looks like this? Nope. However, is there a formula for s over s square plus 5 square? Laplace inverse of, pay attention please, is there a formula for Laplace inverse of s over s square plus 5 square? Yeah, that is cosine of 5t. Cool. Is there a formula for 5 over s square plus 5 square or 1 over s square plus 5 square? Yeah, that involves sine of 5t, right? So if in the denominator we were to have s square plus 5 square, then we are in business, right? So could we think in terms of some shift? S has been shifted by s plus 3, right? So we can think of the denominator as s square plus 5 square, but a shift s shifted by s plus 3 has been applied to it. Did you get that? Please pay attention to that part. Just the denominator itself, focus on it. Can we say that is s square plus 5 square to which a shift of s shifted by s plus 3 has been applied? Yes, right? But then wait a minute, be a tad careful. Don't jump to it. Do not say that is 2s plus 5 over s square plus 5 square to which a shift s shifted by s plus 3 has been applied. Because you have to apply the same shift s shifted by s plus 3 to the top also. But the top doesn't have an s plus 3. That's the problem. That's a small problem. So can we do something where we in fact get an s plus 3 even on the top, right? So what if I were to say 2 times s plus 3? Okay, I factor out a 2, and because we need an s plus 3, I'll say 2 times s plus 3. But wait a minute, that is 2s plus 6. We are supposed to have only 2s plus 5. No big deal. we'll be clever about it and subtract a 1. See how cool that is? So now we have, we can say, yep, this is nothing but 2s minus 1 over s square plus 5 square, to which a shift has been applied, s shifted by s plus 3. It's that manipulation which is key to this problem. And it's based on completing the square to the denominator. Okay? All right. And then, yeah, we can split this into two separate ones and recognize that this is nothing but 2s over s square plus 5 square minus 1 over s square plus 5 square, to which a shift has been applied. How do we account for the shift s plus 3, s shifted by s plus 3? E to the at, right? What is a? Be careful. S shifted by s minus a. So what is a here? Negative 3. Yep. So we'll say e to the negative 3t times Laplace inverse of the inside stuff. Right? I don't need to put s shifted by s plus 3 any longer because I've accounted for that by multiplying by e to the negative 3t. So this is straightforward. 2 cosine 5t and 1/5 sine 5t would be the Laplace inverse of that. That you should know from the last section. Cool? Very important problem. I will definitely ask you a question on this one in a test. It's a 3-star problem. I will change, of course, the numbers and stuff like that, but I'm very, very likely to ask you a question on this. Cool. All right. Let's see. Ooh. So what do we do here? Well, because the denominator is s minus 2 the quantity square, if only it had been s square in the denominator as opposed to s minus 2 the quantity square, I think we would have been in business. So immediately the thought is, let's apply a shift of s shifted by s minus 2. Okay, but notice the top doesn't have an s minus 2, but we will artificially introduce a s minus 2. If the top doesn't have an s minus 2 that we desire, we'll make up 1, but compensate for it. So we'll say 5s instead of 5s. We'll write that as 5 times our required s minus 2. But then that would give 5s minus 10. We need to get rid of minus 10. We do that by adding a 10. Now we'll split this into 2. 5 over s minus 2 plus 10 over s minus 2 the quantity square, and this is nothing but 5 over s plus 10 over s square, to which a shift has been applied. Cool. Laplace. And how do we account for s shifted by s minus 2? Does that look like s shifted by s minus a being 2. So e to the 2t, Laplace inverse of this, and that's 5 plus 10t. Cool? That's the idea. One more problem. Yeah, this is my favorite. What do we do with this? Okay, the denominator is s plus 2. I don't know, for some reason, the moment I see this, I just focus on the denominator. So based on the denominator, we'll think of it as s shifted by s plus 2. Okay. However, we bump into the same issue. The top doesn't have an s plus 2 in it. Right? Can we artificially introduce an s plus 2 on the top? Yeah, we will write that s plus 1 as s plus 2 minus 1. And of course, because it's being squared, we'll add the whole quantity square. Check that out. Okay. Do not simplify the top. in the sense, hey, that's equal to s plus 1. Don't write that. Just leave it as s plus 2, the quantity s plus 2 minus 1, the quantity square. And now look at this as a minus b, the quantity square, and write the expanded version of it. S plus 2, the quantity square, minus 2 times s plus 2 plus 1, like that. And now split it into 3 different fractions. Okay? And think of it as s shifted by s plus 2. 1 over s square minus 2 over s cube plus 1 over s to the 4, s shifted by s plus 2. Cool. How do we account for s shifted by s plus 2? E to the negative 2t. Don't forget that. Times the Laplace inverse of each of these terms. And that's done. Very nice problem. I like this one. So this is also another kind of problem that I will very likely ask you. Cool. All right. Let's move on to the next part. A unit step function. Here's a definition of a unit step function. A unit step function u of t minus a is defined as a piecewise function. U of t minus a is 0 when 0 less than or equal to t less than a, and equal to 1 when t greater than or equal to a. The graph of it looks like this. Cool. So 0, of course, all our functions in Laplace transforms, we already said, will be defined for t greater than or equal to 0, right? So we have 0 to some a. I should have written an a here. 0 to a, and at a it jumps up to 0 to a. This function will have a value of 0, but at a itself, starting at a, it has a value of 1. It's kind of like flipping a switch on. Like if you think of a DC circuit, the moment you flip a switch on, a certain amount of current is flowing, constant amount of current is flowing, then this represents something like that. Okay? All right. And the theorem involving this unit step function is Laplace of f of t minus a u of t minus a equals e to the negative as f of s. Laplace of f of t minus a u of t minus a. This is the second translation theorem. Again, the translation refers to the fact that f of t is being translated to the right by a units with this f of t minus a. That's the whole idea. So Laplace of f of t minus a u of t minus a apparently is e to the negative as f of s. To me, this is not as useful a version as this one. There is a slightly better version of this one that I like. And you must remember this one. Laplace of f of t times u of t minus a as opposed to f of t minus a. So this is a better version because you will see the problems will have some kind of a form like this. They are very less likely to have that form, but they are more likely to have this form. And that's why I'm saying this is a useful version. Is e to the negative as times Laplace of, this is the key, f of t plus a. You would know, please pay attention to this one. The moment you see a problem, you will know what f of t is. What is f of t? Whatever the u of t minus a is multiplying, that is your f of t. And you would know the a itself because you will have something like a u of t minus 2 or u of t minus 3, something like that. So you would know a. When you know f of t and when you know a, can you figure out f of t plus a? Let me repeat that. If you know a and you know f of t, can you figure out f of t plus a? Yeah, we just replace the t with a t plus a. t, whatever a is, let's say a is 2. So you replace a t with a t plus 2. And it is the Laplace of that f of t plus a that you need to multiply this e to the negative as with. Okay, so be careful about that one. I'll show you quite a few problems here based on this one. Okay, let's start with this. Notice, does this look like f of t minus a, u of t minus a? No, it doesn't look like f of t minus a. It's some f of t, u of t minus a. What is a? 3. What is f of t? 3t plus 1. So if f of t is 3t plus 1, what is this saying? We need to find the Laplace of f of t plus a. F of t is 3t plus 1. F of t plus 3. What do you think f of t plus 3 would be? Replace the t with a t plus 3. 3 times t plus 3 plus 1. Right? We note that f of t is 3t plus 1. A is 3. And so Laplace of 3t plus all of this is nothing but e to the negative as, e to the negative 3s, times Laplace of f of t plus 3, which is 3 times t plus 3 plus 1. Cool? So if you really have to understand this one. I'll do a few more examples, but if you need to pause and rewind and go again, please do that. Okay, then it becomes a very simple problem. Laplace of 3t plus 10 is a piece of cake, and so that's the answer. Okay, next. Cool. Does it look like Laplace of f of t, u of t minus a? A is what? Good, pi half. Right. So e to the negative pi half s, sure, times Laplace of sine of t plus a, t plus pi halves. Okay, so that's the idea. But what is sine of t plus pi half? If you remember this something called cofunction, sine of pi half plus theta is equal to positive cosine theta. However, cosine of pi half plus theta is negative sine theta. That's because, second quadrant sine is positive, cosine is negative. So that is one way of doing it. Or if you want to say, hey, this looks like sine of a plus b, which is sine a cosine b plus cosine a sine b, that's perfectly fine too. So sine t cosine of pi half, cosine of pi half is 0. So sine t times 0, that is gone. Cosine t sine of pi half, sine of pi half is 1. Cosine t times 1 is cosine t. So that's what I wrote. Cool. And Laplace of cosine t is piece of cake, s over s squared plus 1. So this is the answer. All right. Let me complicate this a little more. Ooh. What does it look like? Does it look like f of t, u of t minus a? Yep. We know a is 5, e to the 5s times Laplace of, we need to, this is f of t, and so we need to figure out f of t plus 5. So let's do that. Replace t with a t plus 5, and that becomes t plus 5 e to the t plus 2. Okay. How do we find the Laplace of t plus 5 times e to the t plus 2? Any ideas? E to the t plus 2, can we write that as e to the t times e square? And e square is just a constant. Can we pull a constant multiple outside of a Laplace? So do that. And so we have e to the negative 5s plus 2. Where did that come from? That e square that I pulled outside. I included that with e to the negative 5s. Okay. So this is what it boiled down to. Now let's look at this one. Do we know how to find Laplace of t plus 5 times e to the t? Hey, wait a minute. This looks like our first translation theorem, right? Laplace of e to the at f of t is f of s minus a, or Laplace of f of t to which a shift s shifted by s minus a has been applied. So here, let's apply that first translation theorem. A is what? E to the at. Yep, you got it. A is 1. So we'll say that e to the, and Laplace of t plus 5 is this to which a shift has been applied. S shifted by s minus 1. In the next step, we'll replace the s with s minus 1. We're done. Cool? All right. So those were the problems involving Laplace of this, right? Now the question is, how do we do Laplace inverse problems? And for that, let's go back to the original formula we had. Laplace of f of t minus a u of t minus a is e to the negative as f of s. And according to this, it should be this, right? Focus on this one quite a bit. So what is this saying? Laplace inverse of e to the negative as times some f of s. For example, we could have e to the negative 2s times 1 over s square. Can you picture that? E to the negative 2s, 1 over s square. Oh, okay. So we know f of s. We know e to the negative 2s. We know a. Now, what in the world is on the right-hand side? Maybe I'll put it this way. Would we know a? Take a look at that example that I just said. E to the negative 2s times 1 over s square. Would we know a? Yeah, a is 2. Immediately, would you know what u of t minus a is? Yeah, u of t minus 2. Done. So that part of the answer is done. U of t minus 2 in that case. But the question is, what is this f of t minus a? How do we figure that out? Would we know f of s? Yes. What happens if we were to invert f of s? What do we get? We get f of t. But what is here? F of t minus a. Do we know a? Yes. Wait. You would know f of t and you would also know a. From that, can you figure out f of t minus a? Yeah, replace the t with a t minus a. In this case, if a were to be 2, you find f of t and replace t with a t minus 2. End of the story. Right? That's the concept. And we will apply it over and over again. So, Laplace inverse of f of s, right? We would know that. And we apply a shift of t shifted by t minus a. That's what would constitute, all of that part, just that part, constitutes f of t minus a. And we need to multiply that by u of t minus a. Cool? All right, so that's the strategy. I think let's take a break and I'll have a part 2 of this video. That's a good stopping point.